Hey everyone, we will start on top of the hour in around 5 minutes. Thank you for coming. Feel free to check out the paper and the presentation that's in the folder. And we will start soon. And if you like topics like this, feel free to share the room. Hey everyone, we'll start shortly. Thanks for coming. And yeah, as I said, please find the paper and the presentation in the folder. And just as an intro, Victor has found this Hipparchus Star Catalogue, and it has been disappeared, and scientists have spent centuries searching for this. Astronomer. Hi Victor, how are you?
Hi, how are you? I was in the lounge and I hadn't realized I should join this meeting.
Oh yeah, that's our house. The clubhouse made a new feature, different houses, and yeah, that's where the lounge is, and this is a public room from the club. The houses are not public necessarily; they're just only for people that are part of this. So, to explain it a little bit, we have a minute, so. In the beginning, Clubhouse was invitation only app, and a lot of people kind of missed that you can kind of have conversation that are not public for whole social media available. So since they made Clubhouse basically that everyone can join, then they started adding this house feature. So there you need to get an invite to the house, and then you're allowed to chat with people. So yeah, that's the story, I guess.
Awesome.
And there you can chat. Like a lot of people have been then using Discord additionally and switching in between apps around. So I guess that way also they keep the people on this app. So
That's right.
Yeah, I think we can slowly start. I guess people will still be coming in, and this is also recorded, so people will be listening to the replay. But yeah, I think we can slowly start and with introductions and so on, and then go from there. So, welcome to you, Victor. Thank you so much for coming here, making the account, and joining us here on this platform. We really appreciate it. And welcome everyone to Science Society. And before we start, I'll give everyone a short introduction and kind of a short interview so people get to know you a little bit better. And it's a kind of more interactive way to get to know you. So, Victor Gysembergh is research professor, and he has been working on something that scientists have spent centuries searching for, the Hipparchus Star Catalogue that disappeared. Well, so it's a really exciting news, and we are really excited to talk about this with you here personally. And before we start, if you could give us kind of a picture of how did you found out that you wanted to become a researcher and work in this field? Like, what was your path a little bit into finding this curiosity and then making a career out of it? Thank you.
First, thanks for having me. It's a really great opportunity to share some of my excitement about this discovery. I should say that it was very much a collective discovery, but I'll go into the details later on. How did I figure out that I wanted to be a scientist? Um, I was I've always been into books. I loved reading, and I always found, old books particularly attractive for some reason. And so another thing is that I've also always enjoyed learning languages. And when I was 18, I started learning ancient languages like Latin, Greek. I did some other languages, especially ancient Akkadian and Sumerian, which are languages from the ancient Near East, both now extinct. Um, yeah, and it was just a sort of logical thing to do. Do a PhD, and then so my PhD dissertation was on an ancient Greek scientist called Eudoxus of Cnidus, and he wrote about practically every field of knowledge. He was active in the 4th century BC. He was close to Plato and Aristotle, and he wrote about everything: geography, astronomy, mathematics, astrology, medicine, philosophy. Um, yeah, and that's what really got me interested in the ancient astronomy, in the ancient Greek astronomy in particular. That's when I started um, getting passionate, I guess, about these ancient star catalogs. Um, yeah, and I'm fortunate to be able to do that as a job. So I guess I'm really lucky.
Yeah, that's wonderful to hear that 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 it's really always kind of lucky when we think of it, because many people don't have that luck. So yeah, congratulations to that and your discovery. And you kind of already alluded to this specific project, but since this was something people wanted, try to do for centuries, how did it come about that you and your team, you know, were successful. Is there maybe an interesting backstory about it? Did people encourage you to look for it? Did people say, "Oh, we've been looking for so long, why would you find it?" Or was it rather the opposite? I think it's always interesting to hear how these projects came about and became successful.
Yes, it was very serendipitous. So I have been working on ancient star catalogs for maybe 10 years actually, even before I started my PhD. Um, and of course, I would never have dreamed to even witness the recovery of fragments from Hipparchus's Star Catalogue. Um, I would even less have uh, dreamed of being a part of that discovery. Um, so, yeah, what happened is that I've been working since 2020 on a specific type of manuscripts that are called palimpsests. And palimpsests are manuscripts that have been erased um, because their material was very expensive. It's a material called parchment. Parchment is made of animal skins. And so if you look at a volume made of parchments, you're basically looking at a whole herd of animals. So that just gives you an idea of how precious that writing material was. And so it would be recycled. It would be the text would be erased, and people would write on something else. Would write something else on it. Sorry. Um, and for the past couple of years, I'd gotten interested into palimpsests. And so that's an interesting backstory. It was a professor at NYU called Alexander Jones who first suggested that I should have a look at a certain palimpsest in Milan, um, which was already known to contain erased astronomical texts. And I have to say, I mean, maybe I'd read about this manuscript, but I had never actually, noticed it. And so when Alex Jones told me to do this, I uh, I set up a project and I got some imaging done. And soon after that, this was actually during the first lockdown in 2020, at the very onset of the pandemic, we found out that we'd discovered a new astronomical text by Claudius Ptolemy describing an instrument of his called the meteoroscope, which is a sort of armillary sphere. I can go into that, although it's not exactly why I'm here. An armillary sphere, so it's an instrument he can use and that the ancient astronomers use to um, measure stars and planets and all sorts of astronomical measurements. And so, after having set up this first project, which is still ongoing, we were going to publish a paper very soon. We've already announced the text discovery, but we're going to publish a first paper, and we're continuing imaging to really recover as much text as we can from this fascinating document. Um, I got interested into other palimpsests. I guess I was sort of hooked to palimpsests, and I wanted to, it seemed like a good source of discovering um ancient texts that no one knows about because they've been erased. And now we have these amazing new imaging techniques like multispectral imaging that can reveal text that is invisible to the naked eye, basically. So that's the first backstory. And then I remember very well it was during another COVID lockdown in March 2021. Peter Williams from Cambridge in the United Kingdom wrote me an email saying, uh, "Dear Dr. Gysembergh, or whatever, um, I have this astronomical text in a palimpsest. I think it's star coordinates. Would you have time to have a look at it?" And I was very excited to read his email, and I immediately said yes, and asked also Emmanuel Zing, who was working with me in the palimpsest project, to take some time and look at this together. And it turned out to be Hipparchus.
Wow, that's kind of a really amazing story. Thank you for sharing that. And Yeah, thank you so much. And for everyone, I pinned on top the link to a Google Drive folder where you can find the paper and also the presentation that Victor will use um, for the presentation. And yeah, feel free to ask questions, comment in the chat, or raise your hand. And yeah, thank you, Victor. And the stage is yours, basically. Thank you.
Awesome. Thanks again for the introduction. And um, hello to those who have just joined us. And I'm very happy to be able to share some of this with you. So I'll be talking about new evidence for Hipparchus' star catalog revealed by multispectral imaging. There's a slideshow that I've put online, that Katerina has kindly put online. Some of the slides are numbered. I'm just noticing that the numbers are a little bit erratic for some reason. Um, so, as I was saying, Hipparchus was an ancient astronomer who was working in the 2nd century before the Common Era, the 2nd century BC. He was a Greek. He's widely considered as the greatest ancient astronomer. There's certainly, I mean, it's always kind of silly to have to hold these sorts of contests. He was one of the greatest ancient astronomers, certainly. A lot of the other ancient astronomers have remained anonymous, so I'm not here to claim who is the best. But you can see on the first slide um, a modern reconstruction of him working in Alexandria. So Hipparchus was born in Nicaea, which is in present-day Turkey, but he was active most of his professional career as an astronomer either in Rhodes, which is on an island in the eastern Mediterranean, or in Alexandria, where the famous Library of Alexandria was in activity, and so he was likely connected to this unique cultural institution that brought together scholars from different cities and cultures in a quest for knowledge. Um, this modern reconstruction is very imaginative, but you can notice some very interesting features that give you a good general idea. Um, you see the bearded Hipparchus with the beard being a classic ancient Greek symbol for wisdom and knowledge. You see in the middle his armillary sphere. I mentioned these. Armillary spheres are sort of concentric rings that can be used to model the motions of the heavenly bodies or to measure the same motions and the positions of the stars and the planets, etc. So you see him next to this very typical astronomical instrument. You see also a star globe because Hipparchus is famous, among other things, for his star catalog, which went lost, and which we were fortunate to recover some fragments of. Um, and of course, you see this Egyptian decor because he is in Alexandria in Egypt. And you also see him holding a sort of compass, which symbolizes, I guess, his work also in trigonometry and mathematics. Um, he's famous for inventing the first, or for putting together the first table of chords, which is basically the first trigonometric table in the history of science. Um, so this is all just to set the stage of who Hipparchus was. On the next slide, which is number 3, you see an ancient Greek coin, which dates from the 3rd century of the Common Era, the 3rd century AD. We know when it dates from because we can identify the emperor, the Roman emperor, who is represented on one side, the side that is to the left of this slide that you should be looking at. And this is the reign of emperors Valerian and Gallienus. So we can date it precisely to around 253 to 260 Common Era. This is nearly 5 centuries after Hipparchus' birth, and so it's interesting to note that in his home city of Nicaea, he was still being commemorated over 5 centuries after his birth. And so on the right side of the slide, you see this representation of Hipparchus bearded, seated on some kind of stately seat, and he's looking at what should be a star globe resting on a column. So you need a little bit of imagination to visualize this, but specialists of numismatics, that is the science of studying ancient coins, uh, can reconstruct this sort of scene with absolute confidence based on comparison with other coins. So this is the only ancient iconography, the only ancient visual representation that we have of Hipparchus. This is why I'm showing it, although it's admittedly a bit, you need to stretch your imagination. But it seemed important to show you what we know of Hipparchus and who he was and what he looked like. Because he was an ancient astronomer, we have very little biographical details about him. We're not even exactly sure when he was born or when he died. We're not quite sure where he worked at what time of his life. And we're not sure when he did what he did. Is the Star Catalogue a work of his youth, or did he work on it for decades? This we do not know, for instance. But one Byzantine encyclopedia called the Suda contains a short biographical notice on Hipparchus, describing his life very briefly and listing some of his works. And this is from this entry in the Byzantine encyclopedia / dictionary called the Suda. From this entry, we know that we've known for centuries that he wrote a star catalogue. Now, another thing that I should explain about ancient astronomy is that it was a lot of work to copy a book, because all these manuscripts were copied by hand. And on the other hand, their lifespan of these ancient books was often limited. If you didn't copy a book, after a few centuries, it was gone. Are you still hearing me?
Yes, we are still here.
Yeah,
Thank
you're
you.
audible. Yeah, you are audible.
Okay,
But
awesome.
that
So, because of this, there was a tendency for ancient scientific works to be lost, um, since ancient scribes would only copy what they considered to be the most authoritative. And in terms of astronomy, ancient scribes decided to copy the Almagest of Ptolemy, which was a wonderfully written, very clear, very complete expose of ancient astronomy, written in the 2nd century of the Common Era, so about 4 centuries after Hipparchus. They decided to preserve Ptolemy instead of Hipparchus, because probably it was more practical as a learning textbook, a very advanced textbook, but nonetheless. And because of this, we have lost everything Hipparchus wrote except for one commentary, an astronomical commentary on an astronomical poem called The Phenomena of Aratos. Aratos was a 3rd century BC poet who wrote this description of the heavens, which became an absolute classic in antiquity, both in Greek and in Latin and in other languages. Um, and it was read in every, school room, classroom. Um, they would read Aratos, both for the beautiful language and for the description of the heavens, which everyone should bear in mind. The heavens were absolutely present in everyday life. You just had to look up and you could see all of the constellations much more clearly than in today's night sky, which is heavily polluted by light, and where, if you're in a big city, you really don't see that many stars at all anymore. So everyone would read Aratos, and because of that, commentaries to Aratos' phenomena were written, and Hipparchus wrote one of those. And it's basically thanks to the fame of Aratos that Hipparchus's commentary was preserved. Um, Otherwise, we would have lost all of his writings. Now, Hipparchus' commentary to Aratos contains very many star coordinates because his main goal in the commentary is to confirm or correct the indications of Eratos. And Eratos was describing the heavens as a lot of other ancient Greeks had done before him. He was describing the heavens in a purely qualitative way. He would say things like, the head of constellation X is under the feet of constellations Y. So Hipparchus introduced in his commentary numerical coordinates, precise numerical coordinates expressed in degrees, and taken together with the biographical entry in the Suda, this clearly suggested that Hipparchus had written a star catalogue, because in any case, he had done quite a lot of work measuring precise coordinates for all the fixed stars in the heavens. Now, he probably wasn't the first ancient Greek to measure star coordinates in degree. He certainly wasn't. Um, but the sense was that he was the first astronomer to have done so systematically for all the stars visible to the naked eye. The last reason, the third reason, why scholars have been looking for this star catalogue for centuries is that Ptolemy, in his Almagest, also gives a star catalogue where he lists for over 1,000 stars the longitude and latitude in ecliptical coordinates of that star. Um, and this we have in very many manuscripts. And it also explains why Hipparchus's star catalogue went lost, because it was sort of redundant. Um, when Ptolemy introduces his star catalogue in his Almagest, he makes some comments about Hipparchus that are not very clear in terms of what exactly did he borrow from Hipparchus. And he's been accused of plagiarizing Hipparchus's star catalogue, which is a bit anachronistic. He refers to Hipparchus. He doesn't say how much of Hipparchus's star catalogue he's used. And so it's been one of the ongoing questions in research on ancient astronomy has been, how much did Ptolemy actually owe to Hipparchus? I'll come back to this later, because the new fragments that we were able to find shed some interesting new light on the matter. So because of all this, people had been looking for, or hoping to find, the ancient star catalogue for ages. And there was really nowhere left to look. because um, the usually, I mean, the ancient Greek manuscripts that are extant around the world have been pretty well described. There are checklists and inventories and catalogs that represent, countless hours of work by generations of scholars. So it's fairly unlikely that someone missed such a big scoop as this ancient star catalog. However, palimpsests are another thing entirely because these manuscripts have been recycled by erasing text and writing over it. And so in palimpsests, um, things are invisible to the naked eye, and it's only been about 20 years or 30 years that technology has emerged to make these palimpsested texts, these erased texts, readable again. Now, this on slide number 4 is a picture of a leaf from a manuscript called Codex Climaci Rescriptus. This is the palimpsest manuscript in which we found the fragments from Hipparchus's Star Catalogue. In Codex Climaci Rescriptus, you can see here the overtext, which is in very black ink and also some red ink. And on this leaf, you can also see some of the erased Greek text, especially where there's none of the black ink. You see it very well in sort of grayish. It's sort of faint because it's been erased. So this manuscript, Codex Climaci Rescriptus, has been quite famous among scholars of ancient Greek for over a century because it contains very old. Well, it's. Let me describe its contents. The overtext, as we call it, the dark black ink, is in a language called Syriac. It was written in the 9th or 10th century AD, and it's a monastic text by a certain monk called John Climacus. Now, the undertext comes from different manuscripts. When they were writing the overtext, they recycled leaves from a whole series of ancient manuscripts. And it's been known for over a century that some of the recycled manuscripts in Codex Climaci Rescriptus are very old manuscripts of the Christian Bible, written in ancient Greek, and also, even more remarkably, manuscripts of the Bible written in ancient Aramaic. So this has been immensely interesting for scholars. The manuscript was discovered in Egypt by a woman scholar named Agnes Smith Lewis, and she published an important book called Codex Climaci Rescriptus in 1906. By that time, she and others had brought most of the manuscript back to various places in Europe. The manuscript had been purchased on the antiquities market and had been mainly brought back to Europe. Right. So part of the manuscript was later found in a monastery called St. Catherine's Monastery of Mount Sinai, which is in Egypt on Mount Sinai, near a sacred place to the Christians. And so this monastery has been, throughout antiquity and the Middle Ages, a place where pilgrims of the Christian faith from all over the world would come, and monks would come to settle in the monastery. And so it was a crucible for the circulation, a crossing point for the circulation of manuscripts. And the monastery there contains so many fascinating manuscripts, and they're currently being studied by multispectral imaging. Now, in 2012, the Museum of the Bible, which now owns the largest part of Codex Climac Scriptus, decided to subject it to multispectral imaging. And this was a process that was ongoing for several years. Um, and I remember I had heard reports about this manuscript and reports about the fact that it also contained recycled astronomical pages. So I've said that it's been famous for its biblical content for over a century, but in the 2010s, there were reports that this also contained astronomical texts, and especially that it contained an illustrated copy of the poem Phenomena by Aratos, which I've mentioned earlier. And this in itself is just an amazing discovery to find this ancient poem with illustrations in such an old script, which is, I haven't said this before, but the script is probably 6th century AD. So that's very old as far as Greek manuscripts are concerned. Just an amazing discovery to have Eratos. At this point, I wasn't involved with the manuscript. I just heard reports. But as I mentioned in the introduction, in March 2021, Peter Williams of Tyndale House in Cambridge, in the United Kingdom, he wrote me an email saying that he'd found in Codex Climaci Rescriptus what appeared to be numerical coordinates of stars. And he'd found the notation for a degree, and he had found numbers right after that notation. So they were talking about a number of degrees, and in an astronomical manuscript, it's a good bet that these are star coordinates. And he was looking for people to collaborate with him, and I was immensely grateful that he reached out to me and invited me to collaborate on what turned out to be this discovery. So let me show you a little portion of one of the pages where we found these star coordinates. Now this is the slide just after slide 4, so it should be slide 5, but I don't see a 5 on the page. Apologies. Where you can see a close-up of the text, and this is just basically a normal photography. It was made with a multispectral camera, but it's a good color photography of the manuscript. So this is what you would see with the naked eye, and you see these black characters, which are Syriac. So this is the overtext, and you see a little bit of show-through of Syriac from the other side, and this is something that happens all the time with parchment. I mean, you see it on your books as well. Sometimes you can notice a bit of the ink showing through from the other side. So this is just to give you an idea of how little of the erased text you can see with the naked eye. Even the most experienced scholar of Greek manuscript would probably not have guessed that there was even any Greek text here. Now on the next slide, which should be number 6, you see a beautiful, I have to say this is beautiful in several senses, a beautiful multispectral image. The codex was imaged by a fantastic team of people from the Early Manuscripts Electronic Library, the Lazarus Project of the University of Rochester, and the Rochester Institute of Technology. And so the images were captured and then they were processed. This one in particular was processed by Keith Knox. And you still see the Syriac text in black. You still see some show through in grayish, but, and this is where it would be nice to have a screen sharing feature, but you can see in red some Greek text poking out. You can see this most clearly in the upper left corner of the image on slide 6. You can see quite clearly something that looks like an O, and you can see two characters that look like a Y. The O is what we call in Greek an omicron, and the Y is what we call an upsilon. These I think anyone can see. Um, a lot of other characters appear more or less faintly, so depending on how well versed you are in the art of Greek paleography, which is the study of ancient Greek writings, you can read quite a lot. And so we were able to work with a variety of such images. This is just a sample. And in this way, if you look on slide number 7, you will see what we were able to trace. These are the first lines of the first column on folio 53V. So that's how we number the pages. There we call them folios, and there's 53 recto and 53 verso um, for both sides of folio 53. But that's not important. The important bit is that we were able to read Peter Williams, Emmanuel Zing, and I from the images by this fantastic imaging team. We were able to read a lot of the text. I have to say, even on this page, we haven't yet read everything, but what we've read is enough to reconstruct all of the information um, in the text. Um, and so, what can I say? This is just so. This is just to show you the methodology of So we trace um, in a very old-fashioned way somehow. Like ancient scribes would copy their text, we trace what we see. We're a lot slower than the ancient scribes because we have to contend with the fact that the text has been erased. So these letters where you have horizontal bars above them, those are the numbers. That might be an interesting feature. And so sometimes the text is telling us how broad or how wide a constellation is. Sometimes he's giving us the the measurements of a so the specific coordinate, like the declination, for instance, of a specific star, and they describe the star as the left or the outermost on the constellation or whatnot. If you look at the last line here, you see a character that looks like an M with a little circle above it, and then something that looks like an N, and something that looks like an E with a horizontal bar above the N and E. This is interesting because those are the characters that allowed Peter to guess we were dealing with astronomical coordinates. The M with a little circle above it is the abbreviation for degrees, in Greek moirai, and NE is the numeral because in Greek numbers are written with alphabetical letters. It's the number. I shouldn't. I should try not to make a mistake here. It's the number 55. New epsilon with a bar above it. So that's just for the backstory of how we discovered this. Now, it was one thing to read as much as we could, but it was another thing to realize what the text was about. Now, since when it became clear that we really had a whole section on star coordinates, I suggested that the coordinates were by Hipparchus because they were clearly different from the coordinates in Ptolemy's star list. And apart from Ptolemy and Hipparchus, there were no other obvious guesses as to who might be writing. Building up on that hypothesis, we were able to compute what the coordinates for a given star should have been in Hipparchus's time, because these coordinates, they vary over time. Um, they vary over time due to a phenomenon called the precession of the equinoxes, which is not something you'll notice over, a night or even a year, but over centuries you'll certainly notice that the stars are shifting slightly in position. Um, and so this is great in allowing us to date uh, to a certain century given star coordinates. And uh, using this computation, it became immediately clear that we were dealing with something older than Ptolemy's star list, and that what we had was compatible with Hipparchus. Early on in the decipherment, it would have also been compatible with Eratosthenes, who's another famous ancient astronomer, approximately 1 century before Hipparchus in the 3rd century before the Common Era. Eratosthenes is not famous for having written a star catalog, so it would have been really quite surprising to have, star coordinates by him. He's not at all associated with anything like that, but it would have been possible. So we had to work some more and decipher more text in order um, to have a better idea of whether this was really Hipparchus's star catalog, or fragments from it. And this is where another very important insight came into play. There's a Latin translation of a very similar text. In fact, a Latin translation called Aratos Latinus of a manuscript that must have been very much like the recycled Greek manuscript that I'm showing you tonight. Well, tonight for me in France, anyways. Um, this Latin translation was made in the 8th century in northern France by people who were not familiar at all with ancient Greek, so they had a hard time understanding what they were translating into Latin. And they were also writing a very irregular Latin with poor grammar and poor spelling. So it's a text that's incredibly hard to make sense of. But in this Aratus Latinus, basically there are sections where he's translating Aratus, sections where they are translating a mythological commentary to Aratus, and for the first 3 constellations, there are sections where they are translating astronomical coordinates from a sort of as a sort of astronomical commentary. They are translating these coordinates, um, and the structure of those sections is exactly the same as in this Greek text. So they first give the width and length of a constellation, meaning its extension in right ascension and co-declination. So its extension east-west and north-south in equatorial coordinates. And then they give the coordinates of the extreme stars. So the westernmost, easternmost, northernmost, and southernmost stars. We have this structure, and it wasn't completely clear in the Aratus Latinus, but comparing that Latin translation with our Greek text, everything became absolutely straightforward. And so that was a huge breakthrough in the decipherment, I think, because dealing with this erased text, it's a lot easier to recognize the characters once you have a good guess what should be there. So sometimes we were able to also to compute what the star's coordinates should have been, and all of a sudden we noticed, a certain numeral that we hadn't been able to recognize before. Um, so that's the story of how we were able to recover and identify these fragments from Hipparchus's Star Catalogue. Uh, before I, well, later on, I'll 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 say a little bit more about the significance of this discovery. But first, I would like to present an, another exciting thing about this work, which is the imaging technology. Um, I should say it's also just a great pleasure to do this work as a team with these photographers, these engineers, these imaging scientists, these scholars of ancient texts, um, from all over the world, because a lot of ancient scholarship is one individual poring over a manuscript or a book. So this teamwork with these fantastic human beings is really also part of the fun. But if you look now on slide number 8, um, which is numbered, you see a photo of a multispectral camera. This is a camera similar to the one used by the team on Codex Climaci Scriptus. It was made by the company Megavision, which specializes in imaging technology for ancient manuscripts. So they have, several models, and it's fantastic technology. Um, and it just gives you a sense of what the imaging sessions are like. There are lights flashing. This one is clearly some sort of ultraviolet or dark blue, um, but it goes all the way into the infrared. Um, and sometimes we have very short exposures of like a second. Sometimes it can last for dozens of seconds, and for let's say for a given page, usually around 50 images are made just for one page at various uh, band of wavelengths. Some of these images measure reflectance of the light. Some of them measure fluorescence, so when the light is re-emitted at a different wavelength. Some are transmissive lighting, so you shine through the page from below, using special lights for that. Some are also raking lights, so you have a very low angle, and this allows some of the material features of the manuscript to pop out sometimes. Um, so with this said, you understand that it's quite a long job to image a certain manuscript, and you can have a sense also that this technology is not just your run-of-the-mill camera. So it's somewhat expensive technology, and it's labor intensive just to image these manuscripts. To image any given manuscript that has a reasonable length of a few hundred pages, it'll take anywhere between 1 to 2 weeks, because you have to set up the equipment and calibrate it. That's always over one day's work, just setting up. And then you start shooting, and depending on how long the working hours in the library are, it can easily take up to 2 weeks. Once you're home, you have to process the images. Now, again, this is teamwork, and I'm not speaking as someone who can do all of this work fully, although I understand some of it. And if you look at slide 9, you have a screenshot illustrating um, a specific image processing software. It's freeware called Hoku. This was developed by Keith Knox, of the Early Manuscripts Electronic Library, specifically to process multispectral images of manuscripts in order to recover text that has been erased or is otherwise illegible. And it's freely distributed online. It's on GitHub, I think, and on this website of the Rochester Institute of Technology. Um, it's really easy to install, and there's a great tutorial. And I really invite anyone who has an interest in imaging science to, play around with this, because one of the things we really need is people who can process images. Um, and who, it's a very creative job, because or occupation, because every page is a new challenge. Now, over the years, Keith Knox and Roger Easton and others have developed a series of techniques that work fairly well, but we still meet new challenges in almost every manuscript. And so it's very labor intensive, even more so than capturing the images. And it's also very exciting research where you can really discover new methods, and the 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 outcome being discovering exciting ancient texts. So that's the Hoku webpage. Here's just a little screenshot of my Hoku desktop. So you can see it's on slide number 10. You can see that Hoku has these various functions. So basically, you start by reading image data into the buffer, memory buffer, and then you can apply all sorts of transformations. Like you can blur the image, or you can rotate it, you can sharpen it, you can apply mathematical operations like dividing an image by another image. You can apply statistical methods like PCA, principal component analysis, which often reveals text that you wouldn't otherwise see. And you can build whole jobs where you will, apply dozens of these modules to a selection of images and make something that's all of a sudden really easy to read. So there are other software that are used. Especially, there's a commercial software called Envy, which was developed for Earth observation sciences, basically, and which has been sort of, you know, uh, used as a incidentally on manuscripts, and which is very powerful, very useful as well. Unfortunately, quite expensive, so just purchasing the license is sometimes a problem. Um, and so I should say, one of the things I've been playing around with, one of the ideas is the idea that it would be possible to crowdsource some of this work, if people would enjoy that, from various backgrounds. And I think this platform brings people together from a lot of different scientific and non-scientific backgrounds. Um, it would certainly be fun to crowdsource, and there could be just a sort of yearly contest of, yeah, if whoever processes this page of this terribly hard to read manuscript, the whoever does the best processing gets eternal fame, or whatever reward. Um, yeah, so that's something that would be, and I say this because I know that in astronomy and modern astronomy, for instance, there's a lot of crowdsourcing of the huge image processing work that is required. Also, because when you start running the statistical methods like PCA, this just requires a lot of computer time. So it's not just a matter of being creative, it's also a matter of just putting in the time and having the computers run 24/7. So it might make sense to crowdsource some of this. I mean, the people who do the image processing also think so. Um, right. So just these are slides by Keith Knox that I've borrowed. Um, so one of the founders, really, with Roger Easton, of image processing and multispectral imaging, multispectral image processing for recovery of ancient writings. Um, it's just good to have this in mind on slide. So it goes back to 9. Uh, After 10, it goes back to 9. Apologies. Um, there are 3 steps. You capture the image, which is what we do with the camera. So, of course, you can have a better camera or a not so good camera. What matters the most are resolution of the camera sensor, of course, but perhaps even more so is the dynamic range of the camera sensor, which means how many different shades of gray you will be able to capture. Or to say it more technically, how many photons can each individual pixel uh, receive before sort of overflowing like a bucket. And so if you can only receive 256 photons and then you overflow, well, you won't have as fine detail of the contrasts in the image as if you had, I don't know, a higher power of photons. And since we're looking at text with very faint differences in contrast because it's been erased, the dynamic range is crucial. It's also important, for instance, there's been experiments to refrigerate the sensor in order to lower the signal to noise ratio. This is commonly done in astronomical sensors, but it's possible to do it on the Earth's surface, of course, and there has been experiments with that. So I won't go too much into detail about the camera technology, but a lot of exciting stuff. After the capture comes the extraction. Now, you use this software. You have to understand how the light interacts with the parchment. And so there's this little drawing above the extract box on the slide, and you can see that sometimes light can go all the way through parchment, but it will zigzag and undergo a lot of strange, um, changes. Another thing that is important to understand is that the ink usually eats through the parchment a little bit. So that's why on this little drawing above the extract box, you have this little nook on the surface of the parchment. That's typically where ink would have eaten through. And so the light coming from below, this is the transmissive lighting, and you see that it won't behave exactly the same if uh, in the place where the ink has been eaten through. And so since it doesn't behave exactly the same, it's liable to reveal text even if the ink is absolutely gone, just because there will be these indentations due to the ink's corrosive, you know, um, acidic chemical composition. Um, you also see how light is reflected or re-emitted, and this varies, of course, due to the indentation. The reflections and the fluorescence will be slightly different, and so you use all of these properties, which I really go over very fast now. You use all of these properties to extract the information by noticing or asking the computer to notice where things are a little different, this meaning erased inked. Finally, you have to display this, and that's um, also very important. Finding a way for the information you extract to be visible to the naked eye on a computer screen. That's not at all trivial, as imaging scientists will explain much better than I can. If you move on to slide 12, this is a lot of the same information. I also borrowed this slide from Keith. So you see again the importance of capture, just an idea that the spectrum that we look at is much larger than the naked eye can see. That's part of the reason why we recover text, is just because we look at wavelengths completely that are completely ignored by the human eye. We do this in the ultraviolet. Usually, we start at maybe 365, maybe a little more towards 300, but mainly the ultraviolet is interesting for the fluorescence, where it re-emits um, where um, the fluorescence happens in the visible spectrum in the blue. And actually, scholars have been using this fluorescence property for over a century. As soon as it was possible to manufacture UV lights, uh, scholars had the idea of shining them at manuscripts, and a lot of the time you can recover a lot of text just by holding a UV flashlight, which is something else that we do because these technologies are not easy to implement. They're costly and time consuming. We spend the time also in libraries with just a UV flashlight, maybe some ultrasweet, and you can look at the manuscripts in that way, and sometimes you already discover a lot of things about the text. And in the infrared, I should say, um, it's an open question as to how far into the infrared it's interesting to go. Now, these manuscripts, of course, it depends what manuscript you're talking about. In the Middle Ages in Europe and the Mediterranean, people would write with iron gall ink um, on parchment. And so it makes a lot of sense to look at the near infrared. And there's comparatively little data about what happens in the farther infrared, let's say beyond 1050 or 1100 nanometers. Um, and maybe there's a little more going on in that farther infrared than was formerly assumed, but it's still very, very useful and most productive to look at the near infrared. It's a whole thing, a whole different thing for these ancient papyri, for instance. These were written, so it's a different writing material. It's a vegetal. I mean, it's a plant-based papyrus is a plant that they turn into a writing material, and generally the scribes wrote with carbon ink. And here the farther infrared is extremely important. So it's so yeah. Um, Enough about that. And just on this same slide to the right, you have an illustration of how light interacts with the manuscripts in several ways. I've mentioned this before, so I won't go into that now. Right. So, uh, really, I can't emphasize enough how much these new imaging technologies can bring forth in terms of manuscript studies. Uh, there are on just in the okay sorry just in Europe and around the Mediterranean, there are certainly thousands of palimpsest manuscripts, so that's hundreds of thousands of pages maybe, um, and a lot of them have not revealed what they contain, and only a tiny fraction have been subjected to multispectral imaging. So it's really the tip of the iceberg, and there's definitely a lot more that can be done to discover more ancient texts. And this technology, it works also, I don't know, on palm leaves, for instance, in the Indian subcontinent, or on on various materials. Um, it's used very frequently too in art history. Um, on murals, on paintings, and it's just tantalizing, very exciting, but also tantalizing to think of all the things we could discover if we could just apply this across the board. I should stress also that it's a non-invasive, non-destructive technology. This is well documented. It really doesn't damage the manuscripts. um, the only, I mean, the main cause of damage when you're imaging a manuscript is just the material handling of turning the pages, and there's liable to something can go wrong if you're gonna turn thousands of pages. You might tear one, but that's the main risk. So it goes to show that it's a fairly non-invasive and non-damaging technology. Um, to close up this section on technology, I should mention that there are also other avenues that merit exploration. The most promising is X-ray fluorescence. So that's entirely different equipment. You can do this in a synchrotron, or you can now do it portably, but it remains to be established if this is actually feasible in terms of imaging, significant amounts of text in the order of several pages. It's so the portable XRF, the portable X-ray fluorescence, has only been used on a few lines of manuscripts, and so this is something I'm working on, is setting up a project to do XRF on, a portable XRF on significant, several pages of a manuscript. And you can certainly recover more text that way. The problem is it's not reasonable to move manuscripts to synchrotrons. It takes up a lot of synchrotron time, which is precious. It's also very dangerous for the manuscript, and frankly, a lot of libraries just won't agree to it. So it's very desirable to have, performing high performance portable X-ray fluorescence technology. There are also other technological avenues that could be explored. I mean, one amazing thing that can be used on certain types of manuscripts is tomography, where you can look beneath the surface. This doesn't really apply to palimpsests, so I won't say too much about it. And so finally, I arrive at just the general significance of this discovery of fragments from Hipparchus' Star Catalogue. Now, to be quite clear and frank, we've discovered coordinates for 15 stars from Hipparchus' catalog. In a sense, that is huge because we went from 0 to 15. But in another sense, that's very little because Hipparchus probably, I mean, a conservative figure is he had recorded between 500 and 1,000 stars. It's probably closer to 1,000, but um, yeah, still, it's a tiny fraction of the whole catalog that we have at the moment. But these are the first direct fragments. Um, Before that, we only had the coordinates in his commentary, which are problematic. And indeed, sometimes from the star catalog, we have coordinates for the same star. And when we compare with the commentary, um, we see that there is a discrepancy. So it's still it's more than ever an open question as to what the commentary coordinates reflect. Were they made before the star catalog, and maybe Hipparchus refined his methodology and then did the whole catalog, or why are there discrepancies like this? Um, right. Another thing I should mention is that we have a very few quotations of coordinates of Hipparchus. For instance, there's one in Ptolemy, um, in his geography, which is important because it confirms the attribution of these new fragments to Hipparchus, because for alpha of the small bear, he gives exactly the same declination. I invite you to move on to slide 13 if you haven't done so, which is a table with the star coordinates. So the two leftmost columns alpha and delta, that's the right ascension, and the co-declination in Hipparchus's star catalog. Um, the co-declination is the opposite of declination, so you measure from the pole instead of measuring from the equator. Um, this is the convention that Hipparchus followed. In today's equatorial coordinates, we do it the other way around, but it's just a matter of subtracting 90 degrees minus x. Um, so um, on this slide number 13, you see the co-declination of alpha Umi Ursae minoris, alpha of the small bear, and this is also given by Ptolemy as the coordinate according to Hipparchus. So that's an important confirmation that I might have mentioned earlier, that I should have mentioned earlier, of the authorship by Hipparchus. But most importantly, what we have in this table is the comparison between Hipparchus' star catalog and Ptolemy's. So the middle columns, alpha Elm and delta Elm, are the coordinates in the Almagest, in the star list in the star catalog in Ptolemy's Almagest. And as you can see, they sometimes match quite well. This is the case with, at the bottom, with the stars from Corona Borealis in particular, which are mostly within, where the coordinates we have are mostly within a few arc minutes of Ptolemy's. So there it's reasonable to assume that Ptolemy used Hipparchus's data. But in other cases, you have significant discrepancies of over 1 degree, and it's reasonable to assume that Ptolemy was using other data. So this gives us very, very precious insight into how ancient astronomers worked. And the fact that they combined several sources of information, probably, so they clearly did use their predecessors' work in terms of, just these records of data, like a star catalog, but they also clearly used at least two sources, and one of these other sources may have been observation. Now, this brings us to the really big questions. Why did Hipparchus undertake to compose a star catalog? How did he do so? These are very open questions. Hipparchus is connected by ancient sources with the discovery of the precession of equinoxes, which I described before as a secular, so over centuries, a shift of the fixed star's coordinates. He seems to have noticed this, and so it would be reasonable to assume that I mean, not only did he notice this, because it's possible that others had noticed it before him, but he's the first to have given a measurement of the speed of precession, which was not the best measurement, but it was pretty good considering that he probably didn't have much old data to go against. So it's reasonable to assume that having had an interest in precession, Hipparchus, excuse me, Hipparchus wanted to record as many coordinates as he could so that his successors in centuries to come would be able to measure precession much more precisely, much better than he did. So that's probably one of the motives. At least it's a reasonable assumption. Again, we don't know the chronology of Hipparchus's work, so maybe he made this catalog before discovering precession, and that's what led him to discover it. As I said, Hipparchus wrote a commentary to the phenomena of Eretos, where he went into detail about a lot of star coordinates. Um, Maybe he started by writing this commentary as a young astronomer trying to make his name for himself. That would have been a fairly reasonable strategy. writing a commentary to a classic poem. Um, and then he sort of decided to expand and refine his methodology and wrote a star catalog. That's another scenario. As a historian, I have to say that I just don't know. I don't have enough hard facts to decide between these two scenarios. There's a third possibility, which is that Hipparchus um, was impressed by something he noticed, a new star, a nova. An ancient Latin author called Pliny the Elder tells us that Hipparchus noticed a nova. And indeed, during his lifetime, we have, I think, another ancient source from China that also records a nova. Um, so that would maybe have prompted him to record all the stars visible to the naked eye in order to ascertain whether there were any new, so that his successors could ascertain whether there were any new stars and at what rate new stars are formed. Because, I mean, if he's seen one during his lifetime, maybe he's missed others. There are so many. Um, so, does a nova happen every century or every year or every 10,000 years? That would be an interesting research question for someone like Hipparchus. So these are the three possible reasons I can think of for composing a star catalog. Of course, there are also more aesthetic and practical reasons. The Greeks were, and Latin, the Romans, and all ancient peoples around the Mediterranean were big fans of star globes. We've, I mean, a few have come down to us. There's the famous Farnese Atlas, which is kept in the museum in Naples. It's a huge star globe um, um, with all the constellations. And there are some miniature star globes that are a few inches in diameter. So the ancient Greeks and Romans liked this sort of thing, and it would have been sensible to provide for someone scientifically minded like Hipparchus, it would have been sensible to provide a list of coordinates and for globe makers to use these as instructions so that they would make an accurate star globe instead of just sort of positioning the constellations more or less like they looked in the sky. And so that would be a practical motive. There's also, of course, an aesthetically pleasing motive of just, capturing the beauty of the night sky in numbers and showing that it's humanly possible to do so, and sort of translating this beauty into numbers. I think that might have appealed to at least some of the ancients, and to their aesthetic sense. Now, um, showing that it's humanly possible, that was really something. And this will be my last point. How did he do this? We'd like to know. Certainly, for an individual, you would need some kind of institutional support, because if we're if we're cataloging 800 stars, it it takes a lot of work. I'm not sure how to quantify the number of hours, and I think the number of hours depends a lot on how many observations he took of every single star. Um, so, one of the major outcomes of our discovery is that Hipparchus's catalog appears to have been very accurate. Indeed, as you can read in the paper that Katerina kindly provided in the Google Drive, um, uh, all of the coordinates that we recovered are precise to within 1 degree. And this is as good as you can get with naked eye astronomy. Again, all of this was done without magnifying lenses, with simple instruments such as an armillary sphere or a sighting tube, maybe a sophisticated sighting tube called a dioptra, but no magnifiers. So you can't do any better than a 1 degree order of magnitude for your errors. And Hipparchus consistently does just that. Ptolemy, in his star list, makes a lot more significant errors. I mean, a lot. He occasionally makes significant errors of several degrees, or records significant errors of several degrees. He may not have been the one who made these errors. Um, so, um, of course, it's possible that in the relatively small sample that we now have of Hipparchus's star catalog, there were only, he didn't make any errors, but the next, the next star that we'll discover, it'll have a huge error, and so he won't seem so accurate anymore. But for the time being, we have to marvel at his accuracy. And what this suggests is that he had to take several measurements of a star to average out any possible mistakes. And so either he spent really a lot of working hours on this, or he had um, anonymous collaborators. Uh, the ancient Mediterranean being a patchwork of slave societies, it's possible that some of these collaborators were slaves. In any case, we really don't know any of these details, but it's very interesting to wonder and to ask ourselves how he accomplished this. Now, to conclude, I should say that we still hope to recover more text from Hipparchus's Star Catalogue. We know there are certain places we want to look for that. Um, and just to give you another example of what, so this is the last slide, it's number 14 in the PDF. Um, one last example, this is a completely different manuscript from Verona, one of the oldest libraries that has been continuously in activity. The chapter library of Verona has been active since the 5th or 6th century AD. And you can see this manuscript is terribly damaged. The upper image is a color image, and you can see that due to the chemicals that have been applied in the 19th century in hopes to read the text, it's now become absolutely illegible. To the left, you can still read a few letters where there were no chemicals, but otherwise it's just black on black. Impossible to read. Yet on the the middle low image, you see a processed image. Multispectral imaging by people, essentially the same team from Early Manuscripts Electronic Library, Lazarus Project of the University of Rochester, and Rochester Institute of Technology. This image was processed by Roger Easton, one of the founders of multispectral imaging for cultural heritage, as I said. And you can read the letters. I think, even without being versed in Latin paleography, everyone will agree that on these first few lines of this image, the letters can be read. And indeed, I provide a tracing of these letters by Emmanuel Zing. Um, yeah, so this is cutting edge in the sense that these manuscripts that were stained with chemicals in the 19th century, they've long been considered lost forever. And just this May, we provided some more evidence that you can read these manuscripts with multispectral imaging, and we were able to identify this text as a lost introduction to the philosophy of Plato. So also very exciting stuff, although it's not exactly the reason I'm here. So I will stop there. And thank you very much for your attention. I apologize for being much too long, and I look forward to any questions.
Well, thank you so much for this amazing talk. Please don't apologize at all. This was really interesting. You gave us such a wonderful overview of the technique, the history behind it, and then also kind of the accuracy of the map. And it was such a wonderful overview that we would never get from just discussing your paper. So this was wonderful. So thank you so much. And I want to invite people to come and ask questions. I know Siva had a question, and then I'll go after Denise and Siva. So yeah, please go ahead, unmute, and ask your questions. Thank you.
Yeah, thank you, Katrina. Thank you for your patience. Yeah, I have few questions. Maybe some of the pseudo questions are maybe not in your neighborhood. Apologize for that. Now, my first question is: so, is there any variation in the analemma? Did you notice over some 50 years or 100 years like that? So, that is my first question.
I'm sorry, I'm not sure I understood the question. Could you please repeat?
So, analemma, right? The precision effect due to precision effect, if we see just in my DP, I just projected that analemma. Is there variation in the measurements of that figure due to, I mean, over some period of time? That is what I'm asking. Yeah, did you understand, Victor?
Sorry, I understand you're asking about the variation of something, but I'm
Analemma,
not sure.
analemma.
Yeah. Um, so analemma is the is a I guess a family of ancient geometrical constructions that were used as a sort of model of the universe, and at the same time they were used to construct sundials.
Yeah, yeah. That is like eight-shaped figure, right?
Yes.
Is there any variation in that over some period of time? That is my doubt.
Yeah, that's a great question, and it's a very difficult one. Um, just a second, I'm home and I just need to tell my wife something. Sorry, this is the perks of working from home. So it's very difficult to reconstruct the history of analemmatic constructions. We have surprisingly little sources. There's a text by Ptolemy on the analemma, and I happen to be working on it with colleagues. It's a text that we have in Latin translation and that we also have in a Greek palimpsest. So we've made images of this, and we'll be writing the text soon. I mean, editing the text soon. Um, well, that's a bit confident. We'll try to edit the text soon. There's a source in Vitruvius. So he's a Latin writer, and he describes uh, analemmatic constructions, but the problem with Vitruvius is that he's not a specialist of astronomy. He was a professional architect, and so his report is problematic and hard to use. And so, to me, to put it bluntly, the analemmas have always been a sort of mysterious subject matter. And well, certainly you're familiar with Neugebauer's History of Ancient Mathematical Astronomy. I'd say that's still the best reference on the subject.
Can you suggest any books to study about this?
Well, yeah, the so Otto Neugebauer, A History of Ancient Mathematical Astronomy, is just such a great overview of ancient astronomy in general, and it's always very prudent and very thorough. So he, of course, he's not always right. No one is, but that's certainly, the best place to start. There's another great book that came out not so long ago, in terms of ancient astronomy, a few years ago, which is by James Evans, and it's called History and Practice of Ancient Astronomy. And it's such an amazing book because he writes these little chapters, and they're meant to be easy to understand because Neugebauer is not easy to understand. Um, and the great thing is at the end of each chapter, there are practical exercises. Um, so he's just told you something about the analemma, and he's going to say, okay, now try drawing an analemma. Or he'll give you some kind of instructions, and so this is really something I would recommend anyone to read: History and Practice of Ancient Astronomy by James Evans.
Yeah, thank you. Maybe the second question is maybe some pseudo kind of question. Uh, from other planets, are there any observations of the sun like this? Uh,
Do you mean, are there observations made from other planets?
yeah, observations of same kind of analemma from other planets. Is there any that kind of discussion or? Yeah, that's what I'm asking.
Ah, um, I guess the short answer is no. I mean, the um, of course there were models of planetary motions um, in the heavens, but there was no interest in how these projected on the Earth. Probably because they didn't emit light. They didn't, not like sunlight. So yeah, no. I guess the answer to that one is no. But it's a great question. I'd never thought about that.
Okay, thank you. One more question can I ask? If time supports. If sun is moving towards the center of galaxy, uh, 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 is there any change in the position of planets revolving around sun?
Okay, that now I'm out asked. I really am not sure. I mean, from I guess just I mean, I'm not a professional astronomer, but from what I understand of Newtonian physics, um, if you're moving in any direction, well, it won't change the positions of objects relative to each other. It'll just change the way you see them, um, their apparent position relative to each other. Now, yeah.
Yeah, thank you.
Well, thank you so much for this interesting discussion. That was really great. Thank you, Siva. Denise, did you have a question? Maybe not right now. Um, it's so interesting how the new technology development enabled this basically, and you discussed a little bit about transitioning to a more portable version. Um, so, and then also the open source helping idea that you have. I think that's really interesting. I would really love to actually, see that happening and participating. So how, like, what technology development do we need to make this portable device? is something, are people probably working on it to make it basically better and more accurate or usable? And then is somebody also working on this open source that civic science community basically can help with deciphering those? That's really interesting.
Yeah. So those are great questions. For the portable XRF, there are prototypes that supposedly, on paper, they could image a few pages of a manuscript in a week. That's still not really fast enough because it means you'd need maybe several months or a year to image one whole manuscript. But it's a lot better than previously, and so we really just need to test these prototypes. And so that's also, it's something that is not trivial. Just finding a library that will accept, securing funding for the people who will be for the equipment and the people who will be working with that equipment, securing funding for someone to look at the images, because I didn't really stress how time consuming it is to look at these images. You spend hours on one image of one page, and then you have 50 more images to look at, and it's practically never ending, virtually never ending, because there are always more images. But so that would just be a matter of, and so I'm working on, setting up a test on a certain palimpsest with XRF, actually on the palimpsest I showed you at the end, the very black one. Another thing would be just matters of engineering. I think for multispectral imaging, it's also the case that, if they can make the components more robust or less expensive, or have a higher dynamic range, this will have an impact on our little research, but also more generally on a lot of things in the world. So that's obviously something that can come from someone in their garage. It can come from someone doing research in a big private company, in a university, and I can't predict when that will happen. The same goes with portable XRF again. I was saying that these new prototypes, they're still not really fast enough. And so basically you need to make them faster by being able to produce better beams of X-rays. And I really don't know how that works. But, it's a matter of engineering to, the thing works, you just need to make it work better. And maybe there's some brilliant insight in fundamental physics that can lead to that, or maybe it's just tightening a screw somewhere. I really don't know. And finally, the crowdsourcing. Well, it's something that comes up in conversations. We should try to crowdsource. And I know there are websites where you can do this. I think the difficulty is that you need, if you want someone to really process images, this person does need to learn quite a lot. It's not just a click and go. In fact, yeah. So it's hard. I still can't quite wrap my mind around it. How to expand the community of people who can do meaningful work processing these images.
Yeah, that's interesting. So I don't know, do you think Google would be interested? Because they have this basically online library where they want to have like every book written in their repository. Or I don't know how exactly they'll name it. Would they be maybe willing to fund like the imaging, and then also the AI, do you think you can, is it too difficult? Is there not enough data sets? But there are quite a lot of images, right, to like train an AI to decipher it fairly well, to maybe do the start, and then like a human has to look over it in the beginning at least. I don't know.
Yeah, so that's two great ideas. The AI, I didn't mention this because I haven't been directly involved with research on AI for this sort of stuff. But someone who's really on point for that is Brent Seals at the University of Kentucky. And clearly there is enough image data to start working with AI. I mean, as I said in the beginning, I started out because I like Latin and Greek. So, I mean, I understand the concept of AI, but I'm not, I mean, it's a steep change for me to really understand how AI works and make it work for this specific purpose. But it's definitely part of the future will be AI. And my group is, the group I'm in is sort of thinking about it, and other people are doing amazing work with AI. Now, Google, yeah, I mean, uh, Google also sort of pops up in conversations. How do you contact Google? I mean, it's typically an organization that has vastly more resources than even the richest North American university. So I think a lot of researchers think, ooh, if I could just pitch this to Google, and it does sound like something that could interest them, but who do you write to?
Well, I could ask. So we had a guest speaker here months ago that collaborated with Google on nuclear fusion, and what they did was their AI team worked on generating a more efficient way of the shape of the fusion reaction. It's kind of usually a donut shape, and you have to keep it in that shape to keep the reaction going. And he collaborated with them. I don't know, maybe I could reach out and ask how he, but it like if Google asks him, or if the other way around, maybe ask for advice. That's the only, like, and then we had the Google researcher here, but it's a quite different type of research. It was about the time crystal, the senior researcher that discovered or made this first time crystal at Google. He was also here, but that I don't know, because that's very different. So so maybe I don't know. I could try to reach out and then see what the answer is.
That would be great. Absolutely. Yeah. Because I mean, I think sometimes a collaboration between universities and corporations can be very stimulating for both. Keith Knox, who I mentioned several times, he used to work for Xerox, and that's as a researcher, and that's how he got the whole thing started. So, absolutely.
Yeah, and I think it would be maybe also interesting for the AI team, because it's kind of a different language that they, and imaging that they don't see too often. To train it on. It's kind of a niche data set that they probably don't have
Absolutely.
usually.
Yeah.
Okay. Yeah. So, well, thank you so much for coming and for for presenting this research in such a broad way, like from all these different levels or dimensions. I think that was so interesting, and it's quite rare that somebody does this that way. So this was really an amazing presentation, and I appreciate it so much, Victor. And yeah, let's stay in touch, and I hope, because I can imagine that also these scripts are they under threat, especially with climate change, and maybe I don't know, conflicts coming in the future due to climate change. Maybe we have to hurry. I don't know. To
Well,
image all of them at least.
conflict is also always possible, and I mean, the manuscripts in the Ukraine, for instance, I have a couple of colleagues working on them. They're not sure what they're going to find after when they go back, but more so, these palimpsests are just so fragile because they've been recycled, erased, and then a lot of them have been stained by these chemicals where the chemical reactions continue to degrade the manuscript. So they are absolutely a threat, and it's absolutely a matter of just preserving uh, humanity's common cultural heritage.
Yeah, I think that's important because we tend to forget we write on paper now and then we digitize everything. But paper is not as fragile. What was the frequency again of, the invention of paper lowered the need for copying frequency quite a lot, right? So just because of that
No, I'm
also.
not so sure about that. Well, and it depends on the type of paper. But most books that we have, I bet in a couple hundred years, they're toast. Whereas parchment is really durable, actually. When it's 1,500 years old, it's under constant threat and it's fragile. But it's made it that long. Paper will never last that long.
Oh,
And
okay.
your hard drive will probably not last that
Yes,
long either.
no.
So that's also an interesting aspect. I didn't go into that, but it's interesting to think about how they chose what material to write on. Papyrus was not so durable, parchment very durable. The British House of Commons used to print their laws and debates on parchment until very recently in the 21st century.
Oh, wow, I didn't know that. That's really interesting. And we will be screwed, right? I mean, we will know nothing if, something happens and all of our servers are erased. Is somebody writing this down on parchment still then? Like
Yeah,
all the knowledge we have? I don't think so. Like
I
we
wonder
will.
the same thing. All of the financial data, all of the, just from one day to the other, what happens if that breaks down?
Yeah, well, that would be, yeah, we would go back to, yeah, I don't know, whenever we were still analog, I guess.
Yeah. That's when
To
they'll
invent.
call me and they'll ask me to write some parchment.
Yes, exactly. Well, we'll see what the future holds. But yeah, this was an amazing discussion. Thank you so much, Victor, and I'll hope you'll come back one day. We'll stay in touch and
Absolutely. Thank you so much for having me. Thank you, everyone, for your attention and your questions. And anyone, if you have more questions, please feel free to write.
yeah, wonderful. Kyle, you came up. Did you want to say bye, thank you, or feel free to say a last comment, and then we'll close the room.
And I just came up here to say thank you. That was an amazing presentation, and I greatly appreciated listening to you since I entered the room. So thank you so much, Victor.
Thank you, Kyle.
Okay, wonderful. Yeah, enjoy your holidays, and thank you so much again. And yeah, have a great evening, and everyone, thanks for coming, interacting. Have a great morning, evening, wherever you are, and I hope I hear you all back soon. Thank you so much.
Happy holidays. Bye.
I'll close the room in 3, 2, 1. Bye, everyone. Happy holidays.
Bye.